Hey there, creative coders! This is Benjamin D. Whiting, and welcome back to the SuperCollider segment of Null-state's interactive digital art tutorial series. Last week we covered arrays in SuperCollider, both as ways of collecting data as well as a means for multi-channel expansion. This week we're going to discuss a bit about how SuperCollider works under the hood, with emphasis on the distinction between client-side and server-side programming. Let's get started. Before we dive into the distinction between client and server-side programming, it's important to understand just what I mean when I refer to SuperCollider. SuperCollider is often described, by myself included, as a programming language centered around synthesis, digital signal processing, and algorithmic music composition. But it's a bit more complex than that. It is actually a suite of applications that includes the following: scythe, the editor that we boot into every time we launch SuperCollider; sclang, the programming language that we've been covering in this tutorial; and scsynth, the sound generating server that takes OSC messages and produces audio or control rate output. Of these three components, scythe is generally considered to be the least essential for working in SuperCollider. In fact, some people choose to eschew it altogether and use dedicated text editors, typically with plugins aiding in the creation of SuperCollider code, when working in the language. This was a particularly common scenario before the contemporary IDE was introduced back in version 3.5 and updated several times with helpful features. I myself dabbled in using the Sublime Text SuperCollider package back in the 3.6 days, but as of 3.7 swiftly switched back to using the IDE as I find features such as the floating windows with argument defaults an indispensable part of the programming process. Conversely, scsynth is often regarded as the most important component of SuperCollider, as it's what is responsible for the output of audio, which is by far the most common application for which the language is utilized. It uses compiled synth-def code to determine what audio and/or control rate data is generated, and responds to OSC messages to determine the scheduling and termination of actions, along with the setting of arguments in synth-defs with control data, the allocation of memory for buffers, and a host of other operations. There is an alternative to scsynth that ships with SuperCollider on macOS and Linux, as well as on earlier 32-bit releases for Windows, called Supernova. In a nutshell, it works much like scsynth, but allows for the use of more than one CPU core. One must explicitly program this into one's code, however, and as we will not be engaging in anything particularly CPU-intensive for the time being, we will be sticking with scsynth. Finally, sclang is also an important component, as it is the language part of the suite itself, which is interpreted into either machine language for synth-defs or OSC messages for everything else when addressing scsynth. It houses a wealth of powerful algorithmic composition tools. It is also capable of implementing control structures, routines, streams, and other kinds of functionality ubiquitous in higher-level programming languages. That said, sclang is technically optional. One can make use of any OSC-capable language to communicate with scsynth. Python is a popular alternative. One can even control scsynth directly from Macs if one so desires. Depending on the language used, however, it can be rather tricky to compile synth-def code readable by scsynth, so even if other languages are used for interfacing with scsynth, synth-defs are still often coded in sclang. There are alternatives to sclang created with scsynth specifically in mind. Overtone, based on Clojure, and title cycles, based on Haskell, are two popular examples. The opposite is technically also true in that one can bypass scsynth altogether and use sclang to interface with and control other sound-generating languages. Using SuperCollider's powerful algorithmic composition tools along with Max MSP is an option. Now that we've covered scsynth and sclang in some detail, let's investigate how they talk to each other. First, it's imperative to discuss what is meant by the client-server model. Some of you may already know, or at least have guessed, that it's a computer networking term, and you'd be right on the money. To illustrate what is meant for those who may not be immediately familiar with this concept, let's look at the model through a more generic lens. Clients and servers both depend on network communication to function effectively. Servers provide, or serve, functionality and resources to devices connected to them via a network. These devices are its clients. Servers can provide their services to more than one client at a time. For instance, NAS, or Network Attached Storage, relies on a central hub serving one or more clients requesting data storage. Clients, on the other hand, do not typically share their resources and are dependent on servers for services to be fulfilled. Returning to a NAS system, computers that access it while connected to the network do not open themselves up for others to access whatever internal storage they may possess. Both scsynth and sclong behave as server and client, respectively. Ever wonder why we've selected something called boot server each episode before working with sound? We need to launch scsynth before any sound can be generated. Until we boot it, the only components that are running are sclong and scide. Client-side code will still work. For example, last episode we were able to initialize and fill arrays with objects like simple numbers. Sound-generating code, on the other hand, is handled exclusively by the server. The server remains active on the network, listening for bytecode to tell it what kinds of sounds to produce, and OSC messages to tell it how and when to produce those sounds. Hold the phone, you might interject. What do you mean when you say it's active on the network? Is this not all happening on the same machine? Even if nothing is leaving your personal computer, a network connection is still being used for inter-application communication of machine code and OSC messages. By default, sclong sends its instructions out over the loopback IP address, 127.0.0.1, where scsynth is listening over port 57120 using the User Datagram Protocol, or UDP. Incidentally, a connection via TCP, or Transmission Control Protocol, is also possible, but typically not necessary or even recommended unless you're dealing with connections outside of one's local area network. And even then, UDP is generally reliable enough for most situations. On the flip side is sclong, which, as mentioned earlier, is considered a client in relation to scsynth. sclong interprets SuperCollider code and passes it along to scsynth, either in the form of compiled synth-def code for desired sound production templates, or interpreted OSC messages to schedule said templates and provide further context as to how they are to be instantiated. It has the capability to further structure how and when communication with the server is handled, using processes that run completely independently of scsynth. sclong is also capable of accepting incoming network connections, though as it is not a server, it is quite exclusive as to the kinds of processes it opens up for remote access. There is a very handy Quark, or SuperCollider extension, called OpenObject that can be used to open the interpreter up for manipulation by other OSC-enabled applications and languages, though such a decision is not without its risks. For this model to work, both the client and server have their distinct roles to play, very little of which are interchangeable. These can be summed up as follows. Server-side programming is responsible for synth-def code generating audio rate and control rate data, instancing synth-defs into individual synth nodes on the server and the freeing of said nodes, dynamically setting parameters or arguments that have been programmed into synth-defs to be modulatable, allocating buffers in memory to store data, including digital audio, and the real-time storage of data into said buffers, ordering and reordering synth nodes to affect signal flow, creating groups of synth nodes to further organize and affect signal flow, and busing audio and control rate data between synth nodes and to and from hardware inputs and outputs. Client-side programming, on the other hand, includes the following: the use of control structures, such as if-then statements, cases, switches, and the like, to determine conditions that would trigger other actions. I'm specifically avoiding using the term event, as event means something quite specific in SuperCollider. The use of routines or streams to produce a schedule of actions based on either the receipt of input triggering a new action or the passage of time. Variables, functions, patterns, which are special classes facilitating algorithmic music composition, sclang class creation, graphic user interfaces or GUIs, and much more, except for what's listed under server-side programming. To avoid long hours of desperate debugging and frustration, it is imperative that the roles of each, along with what kind of code constitutes client and server-side programming, is understood early on when learning the language. The client-server model is a large part of what makes SuperCollider so powerful, but it is also arguably a big reason, possibly the biggest reason, why the language has the reputation of possessing an intimidating learning curve. We will cover the distinction in much greater depth next episode, but for now I invite you to revisit episode 6, the episode on arrays, and to compare the code being evaluated before booting the server to the code being evaluated after booting the server. It should serve to provide some intuitive understanding of the difference between each before diving into it in greater detail. This wraps up our exposition of client and server-side programming. Next week we will be examining common mistakes when coding in each, like the placement of conditional statements within synth-defs, along with strategies for mitigating the limitations of both sides in order to facilitate getting SuperCollider to behave like you want it to behave. In the meantime, please don't forget to hit that like button and subscribe to this channel to show your support for more interactive digital music and art content from us at Null-state. Also, make sure to check out our Facebook page and webpage to stay up to date on all of our upcoming events, workshops, and concerts. The link is in the description below. See you next time!